It's great to be back in Sweden again, in Stockholm. It's been probably about 3 years since I was last here, so it's awesome to return. So this presentation was inspired by some graduate study work I wrapped up in December, where I was studying space systems, basically rocket science. And as I was suffering through a great deal of physics and math, and trying to figure out why a cyber guy was punishing himself with this stuff, I started like, maybe there's a good place and application for cybersecurity to all of this math and physics that I was going through grad school. And as I started digging into that research, I discovered there really is some applications at convergence of rocket science and cybersecurity. So I put together this presentation, and I hope you guys find some value in it. So my initial interest in rocket science started watching Saturday morning cartoons as a kid, and later on, as I started going to college back in early 90s, late 80s, early 90s, I was very fortunate. I had a math tutor who actually worked with Dr. Werner von Braun and was a mathematician that wrote some of the software to track Sputnik, the first satellite that the Russians launched way back many, many years ago. So that was very fortunate, and he used to tell me all the stories about working on rocket science projects as he was tutoring me through my advanced math courses. And then I had a really good math professor, Dr. York, who totally failed me all the time, but he was really merciful and mentored me and taught me a lot about rocket science. And then I got to work for NASA on doing some stuff with the space shuttle, where I installed the first firewalls that were actually protecting the rocket engine control software, where I learned a great deal back in the 90s. And so those things led to me being interested in rocket science back when my youth. Now, as we start talking about space, there's a lot of conversations these days around satellites, especially like DEF CON, Black Hat. I spent the last few years talking about satellites, but I wanted to try to break off and get into the rocket side, and primarily because I had to take 2 courses on it, and I wanted to do something with it. I had to go learn so much about rockets. I had to find some way to get it involved with cybersecurity, so I didn't, waste all that time learning all that. So you have the 4 segments of space, the space segment, up, like a spacecraft, and then the user segment. Think about with user segment like the Viasat hack that was all in the news a couple years ago with Ukraine, and the link segment, which is, your comms links that you hear about being jammed and spoofed a lot. And then the ground system, which is going to be your ground station where, your mission control is, where the satellite, the spacecraft, and the rocket is located. And so from the ground segment, we're going to focus on the launch segment inside the ground segment and do a deep dive into influencing the rocket performance. Specifically, we're going to focus on propulsion, the rocket propulsion system, and how an attacker might look at a rocket in the propulsion system. So if you find yourself involved with a space project here in Sweden, you really want to pay attention to cybersecurity for the whole system of systems, not just, say, the ground station software, but you got to look at everything, all your sensors, the onboard computers, et cetera, that all those trust relationships, that supply chain needs to be looked at. So when we start talking about rockets, when I was doing my grad school work, all I was getting was physics and math and more physics and math, and I wanted to understand, my initial catalyst, I wanted to understand the network comms and the IT systems involved with space. But as things go with academics, they taught what they knew, and they taught me math and physics. And so I had to go back and jump into more of the system of systems side of this on my own. So I started digging into it, and there's a great deal of computers actually on a rocket. You got the navigation systems, the avionics, you got an onboard computer. There could be multiple onboard computers. The really large rockets may have 3 computers in some cases, where they make sure that all 3 of the computers agree with the data that's coming in. So you could have that. You got cameras. You got all kinds of sensors that are basically embedded system computers that are on these rockets. And what, like I said, we're going to focus on is over on the right. We're going to focus on that engine control system that controls the propulsion of the rocket system. And besides the grad school work, that's what I worked on early in my career, was managing the network with a bunch of rocket scientists that actually wrote that code. And my job was, as the network guy, was to protect all that and keep it all operating. And that's where I actually put in my first firewalls back in the 96, 97 on the NASA network. I put in the first firewalls for them on that across that whole network, and built some firewall-to-firewall VPNs. I've learned so much working with that team. And so, but we're going to focus on that engine controller primarily and what's going on with that propulsion system. Try to do a deep dive in that of how we need to secure that and how an attacker might look at that if we're not careful. Now, one thing that's fascinated me watching the news all the time with rocket systems, you hear about all these tests and things like with SpaceX and other rockets being launched, and they may have a launch, and then you hear about that they killed the launch. The rocket started launching, and all of a sudden they blow it up. So I was curious, well, how do they do that? And what they do is they do that with a flight termination system. And from a cybersecurity standpoint, what I found very fascinating, I started doing this research, is the legacy flight termination systems were unencrypted. Everything I've read, the older flight termination systems, totally open, totally unencrypted. Now, the more modern flight termination systems, the AFFS, the automated flight safety systems, they're encrypted. They're going to use pretty strong encryption when they're operating. But the legacy stuff was, so if you had maybe a software-defined radio or other means capabilities, you might have been able to communicate to a rocket and try to make the thing blow up possibly because it was unencrypted. So I found that interesting. Now, before we do dive too deep in, I wanted to give a real quick overview of where all this rocket science stuff started. I was fascinated of how old the research is into rocket science. All of this, I did a whole master's, and nobody ever talked about William Moore. He was a mathematician out of the UK in the early 1800s, and he published 3 papers that I was able to identify around rocket science, which his research, of course, is going to be based on Isaac Newton's 3 laws of motion. And everybody's heard of Isaac Newton, especially if you've had calculus, you've suffered through Newton's calculus. But Newton, everything in rocket science, and the initial basis is going to be on those 3 laws of motion. And then I'm going to focus on this gentleman, Konstantin Tsiolkovsky, a Russian gentleman, in his ideal rocket equation that everybody uses to define how rocket systems actually work. And we're going to look at it from a cyber standpoint. How can an attacker go after Tsiolkovsky's ideal rocket equation and influence things? Say if we got influence and access to that rocket, either through the supply chain or we were able to get some kind of remote access, what could we do with that rocket? So now, again, going back, mentioned Newton. What I wanted to bring your attention to here, over on the upper left-hand side, I want you to look at that, especially if you've had physics, you're familiar with this, very, very basic physics of the force equal mass times acceleration, F equal m times a. But from a rocket science standpoint, right above the F equal m times a, we're going to look at the change in velocity, that V1 minus V0. So that's the change in velocity. And it's going to be divided by the change in time at T1 minus T0. And that refers to what we're going to focus on influencing, called the delta V. And but it breaks down to just F equal m times a. You know, it's very, very, very basic algebra. So when we talk about rocket science, you can get in some really, really complicated math, but the foundational materials of like rocket propulsion isn't that hard. It's not that hard. You can go and get into the calculus and the differential equations, but to get a basic understanding, you don't have to go that deep. And so here's the rocket equation. We're going to, from a cyber standpoint, we're going to dive deeper into this, but I want to lay a foundation of where we're going, because I had to learn it, and I want to share how being a professional hacker. I got into hacking in '99, and so this is how I look at a rocket, with being in the cybersecurity industry all these years. I'm looking at it. So you got this delta V. And this equation breaks down overall to the right where you got this something called the specific impulse, the ISP, that's the specific impulse. And that's basically the efficiency of the rocket, how efficient the thrust is on the rocket. And that's going to be times that G0 is gravity with the natural log of the mass flow rate, basically the flow rate of the fuel coming out of the rocket. And so that's what we're going to look at. And I mentioned the delta V, what that means and why it's useful. And I'm going to give some real world examples of this where there was some activity that some folks believe that their rockets were hacked because this delta V I mentioned earlier with the Newton equation, that force equal m times a. So what happens with this delta V is the delta V is that change in velocity, how much velocity speed that rocket is going to need to get into orbit. You got so much mass, so much fuel, payloads on that rocket. Well, how much acceleration, how much velocity are we going to need to get that rocket into, say, low Earth orbit, which would be this green circle, and then go into the red, at the top there, how much fuel are we going to need? How much delta V are we going to need to be able to get it, say, in an orbit of like the moon or Mars or Geo or some other orbit? How much power are we going to need? So that gets back to that delta V. And what we're going to break down in the next slides is that equation at the top. We're going to look at from a hacking standpoint, how can we influence those variables to possibly influence the performance of a rocket? Because rockets are rockets. And they're going to be working under these fundamental laws of physics. So now we jump into the cybersecurity side of this. This is what, we were at a cybersecurity conference, so let's get into cybersecurity. So we could go after some software vulnerabilities. Primarily the vulnerabilities you're going to look at with a rocket is going to be pre-launch. Rockets are not going to be running IPv4 and IPv6. You're not going to telnet or SSH to a rocket, any rocket that I'm aware of. You're not going to be going to getting a remote shell, doing a Windows RDP session to the rocket. So most likely it's going to be to the left of launch where something has happened. Compromised insider, supply chain, they're going to mess with your software. After launch, could be that, like I'm reading in the news, there's all these activities with GPS spoofing happen, the position, navigation, and timing, that that type of influence could affect a rocket after launch because, the rocket's trying to figure out where it is in time and space. And so if somebody's spoofing and they're able to influence that rocket after launch, you could affect the performance of that rocket. It may be force the rocket to burn extra fuel because it's getting off track and it's trying to have to reposition itself because you only got so much fuel and so much time. So you could maybe with jamming, like I said, you read, especially ever since the Ukrainian war started, you hear lots and lots about the jamming and spoofing. So that's a vector. Could do laser, microwave possibly, but maybe going after the sensors. Again, those sensors are computers. Just like IoT devices, think about SCADA, IoT, those sensors are specialized computers. They're looking at the temperature, pressure, fuel, safety, and they're feeding data back to a centralized onboard computer. And like on a larger rocket, these really large, huge rockets, like like go to the moon, they're going to have like 3 computers that are configured to agree on this data and make sure they're getting correct data. And then getting into the propulsion system, this engine control unit that is going to be managing the fuel, the mixture, the oxidizer, and whatever the fuel that you're using. And again, mentioned the supply chain. So going back to those equations again, we're going to look at this delta V. So that MF, so you're going to look at your flow rate there. And that's going to be that mass of that fuel. And so somebody from an aggressor standpoint could be looking at that propellant fuel and try to manipulate the sensors and throw off the computer and feed that main computer is doing the calculations, trying to figure out how the rocket is actually working and where things are in time and space. You could be altering the mixture of the fuel, making the rocket not operate efficiently, but sending bad data to the computer and telling the computer everything's fine, there's nothing to worry about. Everything's operating just as it should, keep on going. But actually there's some kind of chaotic problem possibly happening to make that rocket go off course. You can mess with the velocity. Again, we mentioned the guidance, navigation, and control. Maybe like the electronic warfare is happening across large parts of Europe these days with all the spoofing and jamming that's happening to GNSS and GPS. That could be happening, and that could influence these equations of how efficient things are operating. No. Going back to Newton's equation there, that thrust, think of thrust as force that we introduced earlier, that, and in this case, we're looking at the mass flow rate times the exhaust velocity, which is basically mass and acceleration. Let's change the equation a little bit. And you could extend it over to the right, and you could change it and be looking at, break it down to different variables where you're looking at pressure on the rocket environment here. And so those pressure sensors, you're going to be influencing the calculations that the rocket is sending to that primary onboard computers. Could be one computer, could be 3 computers, or just 2 computers, depending on the rocket design. But you could be manipulating that and influencing the fuel oxidizer mix that's going to the pump and how things are operating, and sending totally erroneous data to the main onboard computer. Onboard computer thinks everything's going good, and you're totally manipulating how things are being mixed, and be spoofing the signaling between the onboard computer and its sensors, and send the rocket off into a bad trajectory or make the thing blow up possibly. Who knows? So I like to look at cybersecurity from, I like to use attack trees. I've read about attack trees back in the early 2000s. Dr. Bruce Snyder published in Dr. Jobs' journal a really good article on attack trees. That's where I learned attack trees, from Dr. Snyder. That's like his 1999 publication that he put out on attack trees. And so I like to communicate everything and break cybersecurity down in the form of an attack tree to make sure I understand and help customers understand what's happening with a problem. So this attack tree we got highlighted over on the left. We could just one scenario. We could go after the primary onboard computer. We can manipulate the thrust during the ascent. And maybe we start messing with this thrust equation, these variables, say the mass flow rate, the exhaust velocity. Like I mentioned, we could be messing with the pressure inside the nozzle and outside, and totally throw off the rocket. You know, you could, like mentioned, being able to go and influence the GPS, et cetera. But another scenario mentioned flight termination system. Maybe we go after the flight termination system over on the far right. Maybe we go in through mission control. We have an insider threat. I'm about totally exhausted mentally after being in the cybersecurity business since '96, of having the tired argument that there's no insider threat. There's an insider threat. There's always someone that can be turned and having a bad day and start making really bad life choices for whatever reason. So maybe we have someone in mission control, and they have access to the network. They have access to send commands, and possibly they could use that trusted access to send a command to the flight termination system and try to blow up the rocket. Because what's happening with that flight termination system is it has a belt around the rocket that talks to that little computer for the flight termination system. And if they can communicate to that flight termination system, it's going to communicate to that belt and blow the rocket up. So maybe they could do that. Or if you're using a legacy flight termination system that does not have encryption, maybe someone could use a software-defined radio to try to send a signal. So it's, again, the mitigation, it's going to be important to use encryption just for this case. So how are we going to secure it? In the U.S., a lot of the conferences around the world, everybody's talking about zero trust. You either got to have a zero trust slide or an AI machine learning slide. Well, here's my zero trust slide. And here's my thoughts about how to take some of the concepts, not all of the concepts of zero trust, but some of them, and apply them to a rocket. The flight control system, these avionics, the payload, the communications, the propulsion, those are all very deterministic systems. They're going to have very specific trust relationships and dependencies of how they should be communicating. It's not going to be like an enterprise in the wild, wild west with lots of servers and users communicating. It's going to be very engineered. What sensor needs to talk to a controller, or sensors that need to talk to each other. That's going to be should be very well defined in the initial systems engineering documentation. And in my mind, there should be a traffic matrix that defines what these traffic flows should be in the network on that rocket, locked down, very, very strict, very, very controlled of what those trust relationships are and what's going to be permitted, and not just assume that everything's going to work like it's supposed to, that there's no adversary, because there could be. So we want to lock that down. Now, and of course, you're going to want all this air gapped and that mission control system to be very strictly need to know, vetted access of whoever is going to be trusted to be in the mission control system, the ground station operating the rockets. But thinking from a zero trust standpoint, what I started looking at is I started thinking initially old school, it's probably going to be more of kind of like some kind of serial comms or some kind of open bus technology that they're using on the rockets. But now, what I'm reading now, it supports the zero trust concept, is they're moving to an Ethernet bus called time-triggered Ethernet. And this is actually being used. Some of the new, more commercial, higher-end rockets, some of the new stuff that NASA's uses this bus called time-triggered Ethernet. As an old-school telecom person, that's what I cut my teeth on, was telecom service provider. I was like, time, I know about time. I was like, what they're looking at is taking like the benefits, the capabilities of time division multiplexing, where things are very predetermined and guaranteed time slots of communication, taking that concept of dedicating time slots for comms and applying it to Ethernet for this rocket bus. And so if we're moving to Ethernet, we could go and use software-defined networking, and we could, at the main computer, could very easily lock down those trust relationships and those traffic flows, especially if we have the systems engineering requirements nailed down. It would be very easy in a software-defined network environment on the rocket to have those trusts granularly locked down. And so some real-world examples. As I was digging into this back in grad school and all, and I was like, trying to put this presentation together, and I started figuring out the equation stuff of how a hacker might look at the equation. I started looking, and I was like, has there been anything real? Because I did some presentations, actually came here about 3 years ago and was talking about some real world events with satellites. I was like, has there been anything with rockets? And oddly enough, there is a few. There's nothing like what's in with satellites and what you hear about with ground station issues, but there are some stuff with rockets happening. In the book, The Perfect Storm, this gentleman, David Sanger, publishes that there was a North Korean rocket that was actually disabled in 2012 using a cyber attack. This is a really good book. Highly recommend this book if you're interested in real-world examples of complex cyber attacks. But in his book, he goes into really good detail with regarding this specific attack. Like I said, it goes back to 2012. Also, there is another rocket attack that's documented of an Iranian missile that was knocked down by a cyber attack many years ago. So there's another example of a real-world rocket attack I found fascinating. Doing some further research, those two previous examples, it appears that the rockets got knocked out preemptively, probably on the launch pad early in the process of launching. But in these examples, I found where some individuals over in Russia were talking about that they had two rockets that successfully launched, and they got into orbit. They got into like low Earth orbit. They got into an Earth orbit, and then that's where they would kick in, where I was talking about the delta V earlier, where they'd get that last kick of delta V to go onto the next orbit. Maybe it was the moon, maybe it was Mars. In this case, with the Russians, these two rockets were destined to Mars. And in both cases, they got in orbit, but something happened to the propulsion system that they were not able to go and finish the mission and go into the next level of orbit, which goes back to that delta V. The delta V didn't kick into that propulsion system, so they could go on and get into the orbit they needed to be on, the orbit path for Mars. And in both cases, the documentation that's available, they don't have, they did not provide any kind of forensics proof, but their speculation is that it was possibly a security issue that led to these failures. So I found that fascinating. And again, going back to Ukraine, it's all in the news. There's a lot happening there. It's very unfortunate what's happening there right now. The HIMARS rocket system, it was all the jamming I was mentioning earlier that we're hearing about in the news, that I read about before I came over here just for the conference. Earlier in the war, that was being used against this rocket system. Now, if you're interested in space, if you want to dig more into space and cybersecurity, some real good resources. One, I highly recommend everyone knows about MITRE ATT&CK. If you know about MITRE ATT&CK, you're interested in space systems, satellites, rockets, et cetera, highly recommend Aerospace Corporation Sparta framework. Think MITRE ATT&CK for space systems. They've done a really good job on this framework. Since we're in Europe, need to talk about European resources. European Space Agency, a real good friend of mine, Antonios, is the head of cybersecurity for European Space Agency, and he's done a fantastic job on building a framework for the European Space Agency. It's very similar to MITRE ATT&CK and Aerospace Corporation's Sparta, called Space Shield. And he does a really good job on this. Like I said, if you're interested in space, I highly recommend you check out Shield. Antonios did a really good job on this. Another good resource, this is a international collaboration. This is a fantastic document. They do a really, really good job on this and go into numerous real-world space threat scenarios. It is totally free. It's out on the internet. It's think of this Consultative Committee for Space Data Systems. Think of them like the ITU or IEEE for space. So there's a large international collaboration of true experts, true rocket scientists, communications experts that have come together and brainstormed and written out real-world issues that they're concerned about and made the whole community aware of. Fantastic document if you're interested in this whole convergence of space and cyber. Now, if you're like me, I love to read a book, especially when I'm flying, sitting in a hotel, traveling around the world. I like to have a book, and I like to be able to go and highlight and write into margins and things like that. So that's just me. Some people like to read everything online. I like a book. I'm just old. I like my books. So there's some new books that are out that I don't have listed here. I need to go and update this because there's been a few more books released here recently. But here's 4 that I have that are really good. That one in the bottom right-hand corner, that cybersecurity for space, that's a personal friend wrote that, Dr. Jacob Oakley. He's done a good job with that, and he's updated that book. He's got a new version of that book. And this gentleman up in the upper right-hand corner, Adam, he's done a really good job with his book. It's dated, but there's a lot of really good historic information about space systems and cybersecurity. Highly recommend that book. A lot of his information, if you look up the author, Adam has got a lot of paper. He's got some really good papers that are published as well, so you don't have to buy the book. You could get his papers online. And so, but these are some good books for you to look at. So that is information I had to share with you. I hope it was useful to you. It was quite a painful experience getting to this point of having to suffer through all that math homework. As an old school cyber guy, to get to this point. But I learned a whole lot doing the research. I hope maybe you guys have got something out of it. It'll be useful to you in your career, especially if you work in the aerospace industry.
I'm going to do questions.
Okay, y'all got any questions?
So if you've got any questions, if you could come up here towards the front, these two corridors here, and we've got some folks with microphones here who can make sure your questions get heard by everybody. Questions. Is that stretching or is that a question? So I'm an old rocket scientist, for real. I did Earth and space science.
Okay.
And one of my good friends from university was on the software team for Ariane 5.
Oh, wow.
Which, where they stuck a 64-bit floating point number into a 16-bit hole, and then basically managed to overwrite a bunch of fairly important values, which then made the main engine go basically hard over as far as it could go, resulting in the rocket tipping over and the flight termination system triggering.
Right.
So that is a real-world example of how this shit goes.
That's right.
You know, and the other thing that is worth bearing in mind as well about all of these is that this is the most real-time shit ever. How many people here have ever done real-time operating system-based stuff? Some of you, right, yeah. So, yeah, memory protection. Whatever. Garbage cleanup? Nah. So, yeah, are there any questions? For real? I mean, come on, this is rockets. People love rockets. Shit that explodes, no? Wow, OK, so you've bullied them into submission or stunned silence or something. Right, big hand for Chris.
Appreciate it, thank you.